Hello and welcome to this video. In this video I will hopefully be able to explain how the linear congruential generator works in practice. I will first speak about it theoretically and then I will implement it in Python. Okay, so I want to speak about a class of generators using deterministic recursive functions. And specifically, I want to use the linear congruential generator. And the goal is to create a generator which can generate variables, pseudo-random variables, which are indistinguishable from a standard uniform. So I want to generate some u's which are statistically indistinguishable from a uniform 0-1 distribution. And the way we do this is that we choose a large number m, and then we create a state space 0, 1, 2, all the way up to m. Then we choose a state in which we wish to start and call it S0, and then we create a function f. So we start in S0, then we use f on S0, which brings us to S1. Then we use f again to go to S2, and so on. We continue like that. Now, this is the recursive part of this, that we go to the next step using f. So particularly an Sn will be equal to f of Sn minus 1. And now, since I want to speak about the linear congruential generator, I define my f as a constant a multiplied by s plus a constant b, and then modulo m, where the m is this guy over here. So this is the linear part, and this is the congruential part. Okay, now since we are taking mod m, the result of this function will always be in our state space. So this is great. Now, one thing we have to be aware of is that at some point, since our state space is finite, we will return to S0. I will talk more about this in a moment, but this can be a problem, because now I come to the part where I want to generate my pseudo-random variables. So in each state, except for S0, I want to generate U1, U2, and so on, where I put Ui equal to Si divided by m. And since all my Si's will be in this state space, and I divide by m, then this will be between 0 and 1, which is exactly the state space of the sample space of a standard uniform random variable. So far, so good. Now, it is obvious that if m is too small, if m is 10, for example, then we only have, well, 11 different values of ui, because 0 and then 1 to m. So we generally want m to be a large number. There are multiple reasons for this. As I said, we will at some point return to S0, and the number of steps before we do, we call that the period, and that is dependent on which state we start in. We want to find A, B, and M in a way such that the period is very large for every single starting state. And this is because as soon as we return to S0, then we just repeat the exact same UIs and SIs as we have just done. So we will enter a loop where we will keep repeating the same pseudo-random variables. So we need to have a long time before this happens. And without proof, I will give you some very popular starting settings. We put a equal to 7 to the power of 5, and we put m equal to 2 to the power 31 minus 1, and we put b equal to 0. This is a very famous setting for this linear congruential generator, because here we have the period of size m for all S0. So no matter where we start, we will have to go through all of the states before we return to S0. Okay, now I think this is everything I want to explain. Now I want to show you an example of this in Python. A very quick example. I will use the idle IDE, and okay, so I want to define a function which I call the linear congruential generator, and I will input how many variables I want and my starting position. Okay, so I put a equal to 7 to the power of 5, m equal to the 2 to the power of 31 minus 1, and mind you, this is a huge number. Like I can't see what this is. This is 2 billion and something else. Cool. Then I define f of s as I return a multiplied by s, then plus b, but b is 0, then mod m. Okay. Then I create my output vector. I'll just use a list. That's pretty convenient. Then for I in range up to n, I will first update my s, because as we saw, I don't want to output anything from S0. So before I output anything, I want to update my s. So like this. And then to my list, I wish to add my UI, which is equal to my new s divided by m. And then I simply return this view vector. And this is it. This is how simply we can build a function. And I know that, of course, most programming languages already have a method of simulating uniforms, but this is more to show you that these settings actually work in practice and that it can be done this easily. So I have to save this somewhere. I'll just save it here. Okay, so LCG, if I want to try generating one output, and I just choose a random seed. Okay, with another seed. Okay, well, as we see, these values are between 0 and 1. It's hard to determine whether or not they are uniform, but let me try something else then. LCG, I take maybe 100,000 variables, and I'll just start in state 222, something random. Okay, then I import matplotlib.pyplot as plt. Then I can build a histogram of my use. And as we see, this divides the data into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different bins. And if they were uniform, we would expect the same amount in each bin. And since I simulated 100,000 and we have 10 bins, we would expect around 10,000 in each bin. And well, that's pretty much what we observe. Now, of course, this is not a proof that this actually works. This is just an introduction to the linear congruential generator. You can find resources online where you can see proofs of different settings being statistically indistinguishable. And with that, I mean that, for example, a g-test or a chi-squared test or something similar will not be able to tell that this is not, in fact, standard uniform. So that's something where you take the actual amount in each bin and you subtract the expected amount, and yeah, you can look those tests up. I will not be performing any of those, but I hope this has helped you to understand how the linear congruential generator works. And otherwise, you are welcome to ask questions in the comments below. You are, of course, also very, very welcome to answer any questions others have asked. And then I think this is it for now. So have a nice day and goodbye.